We've been learning about solutions and about bifurcations that occur when we're thinking about first order differential equations, equations of the form x dot equals f of x. And I want to ask the question, given that many physical systems, especially physical systems that come from physics, are actually governed by equations of the form x double dot plus maybe alpha x dot plus f of x equals 0, can our methods of analyzing these first order equations ever be helpful in understanding what's happening in a second order differential equation? And the answer is going to be, what if we have a non-dimensionalized second order differential equation and it looks like this? So epsilon times our second derivative term plus our first derivative term plus f of x equals 0. Well, if epsilon is quite small, then for most values of x double dot and x dot, we can expect that this epsilon x double dot term is basically 0 and we can neglect it. And in that case, we can maybe just analyze these two terms that are generally larger to understand the behavior of the system. This causes a problem because this differential equation actually comes with some initial conditions. So epsilon x double dot plus x dot plus f of x equals 0. X at some point a is equal to some constant xa, and then maybe x at some point b is equal to some constant xb. So that's one possibility for specifying the equation. Because it's a second order differential equation, we need two conditions, because there will be two unknown numbers in the solution function, and so we'll need two conditions to constrain them. So one option is that we're given the value of x at two different points in time, and another option is that we have epsilon x double dot plus x dot plus f of x equals 0, and then we maybe are given x at time 0, and maybe we're also given a value of the derivative at time 0. So these are two different ways to specify the two pieces of information that we'll need to solve for the unknown constants that will come up in our solution. In either of these cases, perhaps you've noticed the problem. If our plan is to neglect this second derivative term, so that the equation we're solving is just 1D and is first order, then we're not going to be able to satisfy both of these conditions simultaneously. We're only going to have one free constant in our solution, and we're only going to be able to satisfy one of these conditions. So, how are we going to deal with this? Basically, away from time 0, very much at all, we're going to be able to use the solution to x dot plus x equals 0, satisfying one of these conditions and not the other. And then close to 0, we're going to kind of not be getting a good estimate of the right answer. And so here I have an example of a particular equation, and here's a solution when epsilon is equal to 0.1. And when epsilon is equal to 0.01, the solution looks like this. And when epsilon is equal to 0.001, the solution looks like this. And so what's happening is we have some solution that's looks a lot like the solution to x dot plus x equals 0 when we're further away from the origin, and very close to the origin we have something sort of crazy happening, sort of within a distance of epsilon of the origin, that allows us to satisfy this second condition. And so actually the solution of x dot plus x equals 0 is e to the negative t, if we set x of 0 equal 1, and that looks like this. So it's essentially an exact match with what's happening at epsilon 0.01 or 0.001. And then for those solutions to satisfy this more full equation with this first derivative condition, they just have this very sharp change that happens right at a short time. Why does it happen at a short time? Why is it that within epsilon of the origin that we have something strange going on? We can think about the size of each of these terms. So this is maybe size epsilon times a characteristic length over time squared, and that's coming from the fact that it's a second derivative, so we're dividing by time twice. And this is length over time, and this is length. And so this second derivative term is going to matter when these two terms are of approximately the same size. So if epsilon x over time squared is of the approximate order of x over time, that happens when epsilon is about equal to time. So when time is quite small, when time is on the order of epsilon, we expect this term and this term to both be of about the same size, and so either neither of them matters or they both matter. And so that's why we have, when we plot the solutions, we have this very narrow region where the solution is doing something strange to meet the second initial condition, and the rest of the time it looks just like a solution to x dot plus x equals 0. And so this type of problem is called, it's called a singular limit. When the highest derivative, term can be neglected, we can't satisfy all the initial conditions. We can't satisfy all conditions. And so this is a singular limit. But that's okay. Even though we can't satisfy all of the conditions, we can still do an analysis that helps us learn something about the behavior of the system, even as we have to neglect one of the conditions.